Hi everybody, I would like to welcome you into this fantastic YouTube channel that's called the Tanzania Online A-Level Secondary Schools in square bracket Olenjolai square or OLENJOLAIM in square brackets. Okay, so you are enjoying the beauty of departments called the Advanced Physics. The subject is Advanced Physics, and the main topic I'll be teaching you today is mechanics. And the topic we are taking a focus on it is gravitation. And this is special for the pre-Form 5, Form 5, or the NTA Level 5, Form 6C, undergraduate students who are pursuing science, teachers, etc., etc., etc. So it's beneficial to different groups of people. However, I will be using the syllabus of United Republic of Tanzania specifically in order to have a focus. But this material can help anybody else around the axis or around the planet S. In case that you want to offer your sense-giving offering, please don't hesitate yourself. You may use this phone number on doing the transaction. If you want to do the banking transactions, please look the descriptions below of this video. You see the bank account. In order to offer your seed offerings, we call it the sense-giving offering, like the way that we are offering to you. So you will be a part of distributing and even providing this knowledge to the thousands of students and teachers and even specialists. So today I'd like to welcome you that in period 7, lecture 7, this is lecture 7 or session 7 or period 7. So whether you call between those names. However, that myself I'll be using frequently on lecture, but you should know that when I say lecture, I mean sessions or period, right? So bear that in your mind. So in this lecture 7, I will be teaching you on problem solving concerning about the satellite motion. I've been teaching you in lecture 4, in lecture 5 and lecture 6. I've been teaching about the planetary motions and the satellite motions. So in this lecture, I'll be solving problems regarding concerning about those concepts. So before I start my today's lecture, I would like to do the quick review of the previous lecture. So in lecture 6, I taught you basically about orbit, right? And in this course of orbit, we say that we have basically two types of orbits. We have free orbits, and also we have parking orbits. So in case of the parking orbit, okay, parking orbit also, we say that this we might call it synchronous, right? Synchronous, or we might call it geostationary parking orbit. Again, I taught you in details about the periods of 40 of the parking orbit or periods of the geostationary satellites. And then we say that the periods, one revolutions will be completed in 1 day. It means that the periods will be 24 hours. So for the geostationary satellites, whether communication satellites or navigation satellites or GPS satellites, that may be to complete 1 revolutions. And then we say that it should be synchronous, means the periods of the satellites should be synchronous with the periods of 40 of Earth's rotations about its own axis, right? In case of derivations of mathematical formula, I taught you basically about how can we determine the height of 40, the height of the satellites, and especially geostationary satellites, or the height of the satellites in the parking orbit. That's what I've been teaching you, and we have derived it. Then we say that is cube root of what? Square of the period times acceleration gravity times radius of the S square over 4 pi square and length minus radius of the S. Again, I taught you about it, the speed, it means the velocity of 40 of geostationary satellites. And then we did the computation for the height. After computation, we found that the height should be set at 60,000 kilometers. For the speed, it will be traveling with 3 kilometers per second. So in case that you want too much details, make sure that you watch lecture or period or sessions 4, 5, and 6 to get too much details about what I've summarized in that sections. So as I said that today it is, this is example. So we'll be having, so the main, the sub, it means that the problem, the subtitle of this lecture is problem solving problem solving, right? Problem solving on satellites motion. On satellites motion. So that's the main focus of this lecture. Now I would like to continue with example. What were the number of example in the previous lectures? Hopeful it was we we solved the 6th problem section. So this example 7, right? So this is example 07. The reference book that I took this question, because when I mentioned these reference books, I encourage you. The reference book, this is Tom Duncan. So I took this question from the book called it Tom Duncan, and the page where I found this question is 184. In case you have it, you have to refer. So then the question says that it is proposed to place a communication satellite in a circular orbit. In a circular orbit around the equator. Around the equator at a height 3.59 exponent 7 meter. So 7 meter above the Earth's surface. Above the Earth's surface, find the period of revolution of the satellites in hours. Find the period of revolution in hours. Okay, find the periods of revolutions of the satellite, of revolution of the satellite in hours. Solution. Let us read the question clear. It's proposed to place a communication satellite, right, in a circular orbit. So the shape of the orbit is circular around the equator at the height of 3.59 exponent 7 meter above the Earth's surface. Find the periods of revolutions of the satellite in hours. So that's the question. Okay, so we might use either of the two formulas that I've taught you in previous lecture. Okay, so we might use the formula that gives us the mass of the Earth. Okay, so let's say, let me just give you too much details. Okay, too much details. We say that given the mass of the Earth is 6. Mass of the Earth, it is 6 exponent 10⁴ kilogram. Universal gravitational constant is 6.67 exponent -11 Newton. It is 6.67 exponent -11 Newton square of the kilograms So, solution. So, you have two alternatives. You might recall the previous formulas if you don't remember. But the basic concept is better for you if you do the quick derivation. And then, as I told you, there's no need for you to claim all of these formulas because you have a lot of formulas. So the first step, we say that derive, okay, the formula, derive the formula that determines sorting period of the satellite. So basically we say that we should recall that we say that period t, this is equal to what? Distance traveled of velocity over velocity. Right? So the period t is equal to the circumference, which is 2 pi, then radius of the s plus h, okay, because we are looking for the period, and then over the velocity. So velocity, here we need velocity of the satellite. So again, you have to recall that we made by using the centimeter force, you can even recall, okay? So that the second step, so suppose that this is the first equation. So the second step, we say that recall, let us recall because I've told you, recall the speed of the satellite, right? So the speed of the satellite, we have two forms. So according to the data that will be given there, we'll record one of the form where we derived. I told you in previous lecture that this is equal to the square root of what? Mass of the s times gravitational constant, and radius of the s plus what? 8h. Okay? So that is the odds. So then this is equation 2. So we go for the third step. So the third step, we say that we have to substitute equation 2 into equation 1. So if we do that substitution, we find that the period of the satellite is equal to what? Is equal to twice pi radius of the s plus the 8h, and then we multiply with what? With the square root of what? Radius of the s plus the 8h, like this, and then divided by what? Divided by the square root of what? Mass of the s times gravitational constant. So period is equal to what? Is equal to twice pi, and then we have the square root of what? Radius of the s plus the 8h cubed, because that if you plug this one into the square root, it will be squared. So squaring, so power 2, so because same base, so power 2 plus 1, then you get power 3. So this is what? Mass of the s times what? Universal gravitational constant. So the period of the satellite will be twice pi, and then we say that what? So this constant also should be given, that the radius of the s. So radius of the s should be given as 6.4 exponent 60 meter. So we say that this is 6.4 exponent 6 meter, and then plus what? Plus the height, which will be given 3.59 exponent 7. So this one should be cubic, then over mass of the s, which is 6 exponent 24, then times universal gravitation of 6.67 exponent negative 11. Right? So then you have to use your scientific calculator to find the period of the revolutions of the satellite in hours, because here you will get in seconds. So you have to change it and express it in hours. Right? So you have 4 pi square, period, okay, 2 pi square, then you have to do that computation. So the period will be, according to that computation, you have to use your scientific calculator properly, and then after you use it quickly, you'll get that period is 86,400 seconds, right? So you know that 1 day or 1 hour, 1 hour is equal to 60 minutes. And this is equal to 3,600 seconds. So we say that 1 hour, so that's all about 30. This is the fourth step. The fourth step means that 1 hour is equal to 3,600 seconds. So how about 86,400 is equal to how many hours? So cross multiplication. So then we have 36,000 or 3600 XE is equal to times X is equal to 86,400. So XE, so then that we cancel this, and then you have what X is equal to 86,4 or 36. So if you do your computations, you do these divisions, this is 2. So you have 72, 86 minus 72, it remains is 100, it remains 14, right? 14, and this 4, it will be 144, so which will be 144 plus 36, you get 4. Because 4 times 6 is 24, you keep 2. And then 4 times 3 it is 12, you keep 2, if you add you get 14. So this is 24 hours, okay, 24 hours. So therefore we say that the period of revolution, the period of revolutions of what? Of satellite is 24. This is 24 hours. Right? So that's the end of solution for example 7. I believe that you enjoyed. In case you have any question, please don't hesitate yourself to go to the comment section and ask your questions as well as you can. So again, we have to solve this, the next problem on satellite motion. And the next problem is a little bit conceptual. It is a concept. So this is example 8. It is concept. It's a new concept that I'm introducing to you. You have to refer to channel 1, or when I say that channel 1, this is class 11, okay? And then the question stating that a satellite travels from the S's, from where? From the S. The satellite, all the satellites are traveling from the S towards the sun. So the astronomers are sending a satellite toward the sun. Given that the distance from the S to the sun, given that you are the physics student, given that the distance from where? From the S to the Sun is 1.5. So this is 1.5. Is 1.5. 1.5 to 11 meter. And masses of the S masses of the S masses of the S and Sun. Sun are 6.24 kilogram. 6.24 kilogram and 2.30 kilogram respectively. Okay. At what point? What point on its path? On its path is a gravitational force on the satellite is 0. Neglect the effect of the other planet. Neglect the effect of other planets. So read that question carefully. Think about gravitation from the lecture 1 to lecture 7. Then think how are you going to solve that problem. The question states like this one: the satellite travels from the S. So it means that the original or the initial point is the S towards the Sun. Given that the distance from the S to the Sun is 1.5 exponent 11 meters, right? And the masses of the S and the Sun are 6.4 kilograms and 2 exponent 30 kilograms, respectively. It means this is the mass of the S and this is the mass of the Sun, as I told you in previous lecture, and we did the computations together. At what periods on its path? At what period? At what point? Not period. At what point? So this is very important. At what point on its path is gravitational force? Is gravitational force? Is gravitational force? Don't confuse is gravitational potential energy or gravitational kinetic energy or gravitational total energy. We are not talking about energy, we are talking about force. At what point on its path the gravitational force on the satellite is what? 0. Neglecting the effects of other planets. So, think a moment. How can you solve that problem? Because when we be solving problems, we are solving problems because we have already covered the concepts in the previous lecture. So take 30 seconds, take a minute to think. How are you going to imagine that you're in an exam? And that is a final exam. And possibly that's one of the questions that you planned to solve. How are you going to solve this problem? Think a moment. What do you think in your mind? What formulas are you going to use? Are you going to compute the periods? Are you going to compute? What are you going to compute, first of all? What formulas are you going to use? Because you have a lot of formulas in gravitation. Think a moment. If you're watching with your colleague or with somebody else, okay, take a time and discuss. Pause the video. Take a time and discuss yourself. How are you going to go? How are you going to solve these problems? Imagine that I have concluded, I have ended all the lectures of gravitation. I didn't touch about this problem. So how are you going to solve? What do you think? What comes in your mind? Okay, so spend some time. I believe that you spend some time, so let us solve. Let me teach you how are you going to think on this problem. Everything is already covered, but the issue is how questions are a little bit tricks. So the first step you can analyze the data that have been given. That's very important to know what you have been given and what you should find first. So the first step, let us analyze the questions, the data given. The first piece of data to be given is the distance. The distance from where? From the S to the Sun. And this one we can call TR. It is given as 1.5 exponent 11 meter, right? And then the second piece of data that will be given is mass of the S. So mass of the S. Mass of the S we can have to label like this one. This is 6 exponent 24 kilogram. All of this data should be used effectively. Again, we are being given mass of the Sun. This we call TMS is equal to 2 exponent 30 kilogram. Heavy heavenly bodies, right? And hence again we be given, that's all. Then the gravitational force, yes. They be given the gravitational force, the force of gravity, gravitational force. Gravitational force at that point, gravitational force at the desired point is 0 Newton. Right? And then what you have to find is we have to find the distance, because the question is at what point on its path is the gravitational force of the satellite. So the distance of the satellite, the distance of the satellite when its gravitational force of gravity is equal to 0. This is what required. So that's the first step, okay, for the serious physics student. Remember that this channel is for the serious students, and this program is for the serious students. If you are not serious, you are taking physics, A-level physics, not serious, this channel might not be suitable unless that you want to get transformed to become a serious student. Okay? So the second step, we have data. The second step now, we have to sketch the problem. Because when you sketch the problem, we simplify. Sketch the problem. So the way we sketch the problem, okay, so we have a satellite. We have a satellite. Okay, we have a certain satellite is traveling. And this satellite, it has its own radius, right? So we say that is the satellite, it's circular. So possible that it has its own radius. And then we have the Sun as a star, right? As a huge star. And also we have the center. So suppose that this is center O, center of the Sun. So suppose that this is the satellite. And then living from the Earth's surface. And then this is what? The Sun. So we have distance between the centers. The distance, because given that the distance from the S, okay, so we say that this is the S. Yes, okay, this is not a satellite, this is the Earth's surface. Right? The Earth's surface. So here we have the mass of the S, here you have the mass of the Sun. Okay? So, and then we have the distance between the center of the S and the center of the Sun. Okay? So you have distance. So you have the distance between the two centers. Okay? So this distance, okay, we labeled it here as R. So this is R radius. And then the satellite is somewhere else because the satellite is traveling. So suppose that this is the satellite with the certain mass of the satellite, which we call Tm. So we can have even a satellite or ms like this, right? So this satellite is leaving the Earth's surface, traveling towards 40. So this is the trajectory or directions of 40, direction of the satellite toward the sun, right? And then there is a 20 in between this 20. Suppose that this is, okay, this is center, suppose that this is A and this is B, right? So there's a 20 whether near to A or near to B or at the middle of A and B where the gravitational force is 0. What does it mean? This satellite, it is a heavenly body. There's a force of attraction, meaning that the satellite is being attracted by the S. And also the satellite is attracting the S. So the satellite is being attracted by the S. And also the S is being attracted by the satellite. But because this is between the S and the sun, the satellite also is being attracted by the sun, and also the satellite is attracting what? The sun. There is a point whereby these forces, force of attractions, suppose that this is the force of attraction 1, and this is force of attraction 2. Force of attraction 1, listen careful, because this is the point where the secret is. A force of attraction 1 is a force between the S and the satellite. And force of attractions 2 is a force of attractions between the satellite and the sun. Right? So there's a point whereby these forces balances, because these are the vector quantities. So it means that at that point we say that the difference of these forces will be 0. So that will go for the steady state. Steady state, we say that at a certain distance, let's say x from what? From the S. From the S's surface, right? From the S's surface. We say that the force of attraction between the S and the satellite will balance with the force of attractions between the satellite and the sun. So this is a case that we say that, for example, at the beginnings, the force of attraction between the S and the satellite is greater than the force of attraction between the sun and the satellite. So at this point, that's the point whereby the gravitational potential is equal to 0 when these two forces balances. So it means the distance now from the S's surface will be from this point, from the center to this point. So here we say that the distance is x, as we say the distance from the S's surface. So if this distance is x from this point to point C, we can even just extend it to the center of the satellite, so the point C. Then the distance, the remaining distance now from point C to the center of the sun, this will be r minus x. Right? R minus x. So that the distance between the center of the sun and the center of the satellite, r minus x, and the distance from the S's surface to the satellite is x. Center of the satellite, center of the S is x. Center of the satellite, center of the sun is r minus x, because the total distance between the center of the sun and the center of the S is r. So if that's the case now, we say that we have to proceed. I believe you enjoy the beauty of physics. Physics is beautiful. It's not a complicated subject. Okay? It's not an easy subject. It's neither complicated subject nor easy subject. So you have to be serious from the beginnings of learning physics to the end if you want to prosper in physics world. So then the first step. So the first step we say that, okay, so we have to recall the force of attraction between the force of attractions between us and the satellite. So according to Newton's universal gravitational law, we say that the force of attraction is equal to the products of what? Of mass 1 times mass 2 times universal gravitational constant